Hello, my name is David Tarkalson. I'm a soil scientist with the Agricultural Research Service. My presentation today is to show some research that we did in the Northwest US where we applied sugar beet lime to a soil and assessed the effects of that lime application on soil properties and crop production. It's important to note that these soils are already high in pH and did not need lime additions to adjust pH, which traditionally has been why lime is applied on soils that are highly weathered, typically in high rainfall areas where a lot of the basic cations and anions are leached out of the soil. And as the pH lowers, aluminum becomes soluble and affects the roots, particularly the elongation of root cells, and it causes a lot of problems, all the way from water deficiencies to nutrient deficiencies across the whole board. You can see in the lower left-hand side this picture of corn being grown in plots that were not treated with lime and plots that were treated with lime, and just the damaging effect of aluminum, soluble aluminum, on roots themselves. You can see a cross-section of a column demonstration where as pH drops, the aluminum becomes soluble and really starts affecting the roots. It's also been shown that in some areas, in situations, lime applications, irrespective of pH, can dampen and control Phanomyces pressure and root rots. There's also been some indication this may be also applicable in the high pH soils in Idaho as well. This is just a map showing the area that we're talking about here, the amalgamated growing area in the Northwest US. Typically these soils in this area of the Northwest are higher in pH. Many soils have excessive calcium carbonate in them, and there really is not a need to be applying lime to adjust pH. So when we say sugar beet lime, what we're talking about is a material called precipitated calcium carbonate, or PCC as an acronym. And this material is formed during the extraction of sucrose and sugar. Within the sugar beet, part of the process is to get all that pure sucrose removed from everything else. And within the stream, there's a lot of impurities within the sucrose stream, and so that has to be removed so the sucrose can be extracted into sugar. So calcium oxide and carbon dioxide are added to the stream, and the calcium carbonate with the impurities included precipitate out of the stream, and so it can be collected and separated, and this is what we call the PCC. The average constituent concentrations from samples from the PCC in Twin Falls, Idaho show that there's very little available nitrogen, ammonium nitrate, in the lime. There is a significant amount of P2O5 phosphorus at about 37 pounds per ton. There's a small to moderate amount of potassium located in the PCC. There's very little copper and sodium, two constituents that we're a little bit more concerned about with regard to toxicity as well as soil structure issues. And of course there's quite a bit of calcium there because it is a calcium carbonate material. The calcium carbonate equivalency percentage is about 75%, which indicates a very good lime source. And the pH is 8.5 and the EC is 2.5. Here we see the amount of actual PCC in dry tons that we have within the system, in the amalgamated growing area system. We see both the stockpiles of the main factories as well as the annual production of the main factories as well. And so on an annual basis, there's a production of material, and you can see from the stockpile of about 12.5 million dry tons that have been collected, it is being accumulated, and there's not an equal state of that being produced and that being utilized and taken out and having some use. This becomes an issue. So this PCC needs a new location, needs to go somewhere, needs a new home. Amalgamate does not want to keep stockpiling this on land. And there's a couple reasons for this. There's always the potential. There's always the murmurings of there may be some environmental restrictions and guidance on what has to be done with this lime and these piles. And so that potential drives us to determine where can we put this, what can we do with this in an area where we don't necessarily to be adjusting pH with periodic lime applications. Especially in Twin Falls area, the land around that area is very valuable. And so if the land is available, purchasing the land can be costly. If the land's already owned, it is more valuable to have other things done with it than the lime being applied to it. So there's all these particular factors that lead us to want to be able to dispose of this or have some type of place to put this permanently and into the future as well. So in our area where you don't need to actually adjust soil pH, the main place to utilize the PCC or dispose of it is going to be on agricultural land where you're taking the beets from, and other land as well. That really is if you want to get rid of it, if you want to have a place for it to go now and in the future, that's really where it has to go. Lots of agricultural land that can actually utilize the material and take it up. There's going to be a little bit of a need for Aphanomyces control, that disease, and there's areas in the state where that is an issue, and that line can be used to maybe control that, but that amount of land is relatively small compared to the amount of agricultural land that's available. You got to remember there's a large stockpile at each factory that needs to be disposed of, as well as the annual amount that's going to be made available during the processing each year. And so we really wanted to look at the effects of just what's going to happen to crops and soils in this type of disposal method when you're applying it to land that doesn't necessarily need it. You're just trying to get rid of it. If we can show that there's no effect, that's great. If we can show us a positive effect, that's even better. But if there's a negative effect in any manner, then we have to be very careful, and may not be the best option for that material. Now this disposal, it's called that because there's really no need for it to be applied. There's no purpose of it being applied in terms of agronomics. We're not trying to control the pH. We're not trying to control disease on most of this land. Therefore, it really is a disposal. This land doesn't need it. The pH is already high, 7.5 to 8.3. In many of these soils, we already have a high amount of free lime content. Therefore, what we're trying to do with this particular study is determine whether there's any negative effects. If there's some positive effects, we'll figure those out. That would be great. However, we want to see whether there's any negative effects, because even if it's just neutral, there's no effect at all, that's a good thing, because the lime can then be applied without negatively affecting crop production and other factors we're interested in. So here's our study setup. It's located in Kimberly, Idaho, on a Portneuf silt loam, pH around 7.8, 8.0 on average. Excess lime contents, free lime contents of about 4%. So it's an alkaline soil. Our 4 lime treatments were a control. We had no lime. We have a treatment where we applied 3 tons per acre annually for 4 years. That's what we call our 3A treatment, or 3 annual treatment. A 10A treatment, same thing, 10 tons per acre annually for 4 years. And then we have a treatment where we applied 40 tons in the fall before the first crop, so in 1 year only. This is called 40T for 40 total. You can see there that the 40 total and the 10 annual treatments, when it's all said and done after 4 years, will have received the same amount of lime. It was just applied a little bit differently. All this lime was applied in the fall before each crop in the sequence. The rotation was a sugar beet, dry bean, barley rotation, and this study ran for 6 years, so we actually was able to run each crop twice in that rotation through this system. And the study was replicated 4 times for statistical purposes. To give you an idea in terms of a timeline to help you keep things straight in your mind, this goes to show you the cropping plan, where we have the 6 years with the rotation being completed twice. The lime plan, the lime, again, I mentioned the lime was applied in the fall. So in 2014, you had the 3, 10, and 40 application rates applied. The first cropping year was in 2015. So you can see that in the falls following 2014, there's no 40-ton rate because that was only applied once. But you continue to have the 3 and 10 ton per acre rates applied in 15, 16, and 17. And then after that, in 2018, 19, and 20, which is the second half of that rotation, all the lime had been applied. It's going to be applied. And so you have a total of 12 total dry tons per acre on the 3A treatment, 40 tons per acre total on the 10A treatment, and again 40 tons per acre total on the 40T or total treatment. And you can see the final rates there down at the bottom. In terms of measurements each year, of course we measured yield, and in the case of sugar beets we measured other factors, that impurity factors, that were of interest as well. We also sampled the soils each fall and spring within each plot within the top 12 inches to assess some of the soil characteristics as well. So this shows you the amount of the different constituents that we showed earlier with the 3, 10, and 40 ton per acre application rates. Little to no available nitrogen in this material, so the application rates were very low. However, we applied a lot of phosphorus, from 112 all the way up to almost 1,500 pounds per acre of P2O5. It is a significant phosphorus source, which can be a good thing if the phosphorus is needed, or it can be a negative thing, especially if you're on land close to surface water, where runoff or any type of erosion can get into that surface water and go downstream and cause problems. There's a small to medium amount of potassium as well, which is a good thing agronomically if needed. There's very little of the things of concern, the copper and sodium, lots of calcium because it is a calcium carbonate material. Let's now get into our yield data. This is the sugar beet yield and quality data for the 2 years we grew sugar beets, in 2015 and 2000. Let me get my pointer up here. In 2015 and 2018, with comparing the different treatments. I included the cumulative lime application prior to the listed crop, the subsequent crop, so you can look at those right here. We have root yield, ERS yield, or sucrose yield, sucrose concentration, root nitrate, and root conductivity. Okay, and so we have our statistical analysis here, our ANOVA p-values. If these values are less than 0.05, then they are significantly different from each other. If they're not, then there's no differences between the treatments. And we can see in 2015, there was no difference across all those measurements between the different treatments. Therefore, the lime did not significantly change those compared to the control, which is a good thing. There was no negative effects. However, in 2018, there was one factor, the root yield, where we had a higher yield for the 10-ton treatment compared to the control. However, the other two lime application rates were not different than the control. This is not very easily explainable. It may have been due to phosphorus potentially. However, the data indicates that may not be what it is, because we already have sufficient phosphorus in the soil with the control treatment to provide enough for the crop. And the 40-ton treatment and the 3-ton treatment were not different than the control. So we don't know exactly what caused this. Sometimes you see these things and you can't necessarily explain them. However, with the other measurements, there was no difference at all. So the dry bean yield in 2016, 2019, same type of graph, same columns, and you can see the cumulative amounts that were applied during those 2 years going into those crops. 2016, we got a major hailstorm that the crop was destroyed, and we couldn't get yield there. But in 2019, there was no difference in the dry bean yield between the treatments. Barley yield. 2017 and 2020, we can see that in both of those years, across those treatments, there was no significant difference in the yield of barley for those 2 years. So the lime applications did not negatively affect or positively affect the barley yield compared to the control. Let's look at soil pH, what the effect of soil pH is. So these are pHs taken each year in the fall. One thing you can notice, we have the 2014 pre-lime application pH. So this is before we put anything on. You can suspect this is a uniformly treated field. Therefore, there was no treatments out there to affect the pH. And you can see that this NS here, this NS value above those columns in 2014 means not significant. There's really no difference in the pH there. And this same non-significance played out for every single year all the way to 2020. Although you can start seeing that with lime applications, there may be a trend for a little bit of an increase in pH each year with the lime applications compared to the control. However, it's a very small increase and not significant. One thing you can notice in here is that there is a difference in the actual absolute value of the pH over time. So in 2017 on, for whatever reason, the pH level in the soil was just a little bit higher than the previous 3 years. And that's not because we added something or something's different. It's basically probably due to a lot of factors we don't understand. It could be the soil temperature. It could be due to the balance of the hydrogen ion within the soil in relation to a lot of the bases that are in the soil. But that's something that's not an impact from the actual treatments themselves. Well, the one thing that was affected by the PCC was the Olsen phosphorus concentration. So the bicarbonate extractable P, or plant available P, that we have in the soils. You can see that in 2014, before we put anything on, there was really no difference. It was not significantly different between the treatments because we hadn't put anything on yet. This variability here was just variability within the field, and if you did the analysis, they were not significantly different from each other. But after we start putting lime on, then things started separating. You can see that after the first year, right before the second application of lime, the effect of the first lime application becomes evident in the fact that that 40-ton application rate had a much higher phosphorus concentration compared to the other treatments, including the control. In 2016, you can see that the 3-ton and the 10-ton per acre treatment are starting to get elevated and higher than the control, and start approaching the amount the amount of extractable phosphorus as the 40-ton rate as well. And so you can look across 17, 18, 19, and 20 and see that that same pattern continues, whereas the 3-ton rate, which at this point in time in 2018 it had 12 tons applied, it's not quite as high as the 10 and the 40 treatment, but it's significantly higher than the control. You can also see the control is increasing over time as well, and that's because in 2015 in the spring, we put on a big dose of phosphorus fertilizer on the control treatment to minimize this effect from phosphorus on crop yield. So conclusions. The data, and of course we haven't completely finished analyzing the data yet, and we still got more analysis to do. But the preliminary data suggests the land application PCC is a viable option on alkaline soils. So yield, sugar beet quality, pH with the PCC equals the same of those constituents without PCC. The one thing that we did notice is that PCC is a very good phosphorus source, and that needs to be accounted for in your applications. And of course, we have more data that needs to be analyzed, more soil data we need to analyze to see if there's any potential negative or positive effects from the PCC application. With that, I say thank you. And if you ever need to contact me, want to talk about this, just get a hold of me at this email address, and I will respond, and we can correspond by email or talk via phone. Thank you very much.